Let's begin our look at weather and ultimately climate by identifying some important qualities of the definition of each. When we're talking about weather, in this case, we're referring to the conditions of the atmosphere at any given time and place. The timetable for weather is the shortest of the two. When we look at a concept like climate, the timetable is long term. In this case, it can be decades, centuries, or even millennia. For our purposes, we can consider climate to be patterns of weather over many years, including extremes and everything in between. The pattern that we see emerging over these long-term periods becomes climate, or how we classify or categorize patterns of weather over these very long sections of time. So when you think about these two concepts, they are very much linked to one another, whether it's being phenomena associated with the troposphere, or that they are, in a sense, really describing or looking at the same thing. The only thing that really is different about these two definitions is time. And it is for this reason that when we are looking at how something like climate might be changing over time, we really can't localize, or we can't restrict ourselves just to looking at a recent pattern of weather or comparing one season and its patterns of weather to the next. We need more time. The climatic maps that you will be looking at and interacting with, as well as the descriptions of earthly climates that I will be giving you, are things that are not of the moment. They're things that will, if they change at all, they will change very slowly. And they really represent all of the variability in terms of weather over very long periods of time. Now, with that said, when we look at the global climate system and we engage the notion of systems, what we have to realize is that the global climatic system is categorized as dynamic. It is always in a state of fluctuation and change. Today, climatologists demonstrate that there are many linkages that exist between the Earth, its atmosphere, and its hydrosphere. Those interactions, their volatility, their change over time, and ultimately all of the different patterns that we can measure and recognize within them and attempt to predict, these are things that become the building blocks of climate. So to add to our understanding of climate, one of the things that we have to make sure to keep in mind is that climate is more than just a consideration or a record of simple averages for temperature and precipitation. It is a network, it's a web, it's a series of interactions between a variety of naturally occurring phenomena within the Earth's system. And climate, as is the case with the smaller scale phenomenon of weather, is really a byproduct of how the Earth relates to the Sun over an annual cycle and, of course, over um, multiple cycles running over centuries or millennia. When, for example, we look at the strong monsoon rain patterns, and these would be patterns of weather associated with geographic regions such as West Africa, we can realize, or we will realize, that these patterns of weather, when we look at them through a larger scale, in this case, when we increase the amount of time and space that we observe them within, are really a phenomenon that are connected to other aspects of the Atlantic Ocean. In fact, the patterns of rainfall that we associate with West Africa between June and September are in fact strongly correlated with what we see between, in this case, August and October along the southwestern seaboard of the United States. Additionally, these two phenomena, the monsoon season of equatorial and subequatorial Africa, both in the north and southern hemispheres, and the storm activities and the hurricane season associated with, in this case, the western edge of the Atlantic and what is considered to be the Caribbean Sea, these two phenomena, as we look at them more closely, are in fact part of a climate, a climactic region that incorporates all of the equatorial and tropical regions of the planet. So the line that divides climate from weather, and I would say an additional line that divides climate, weather, and how we experience the world around us on a daily or even seasonal cycle, is very blurred. And something like an easterly wave, this kind of tropical depression that forms in the Caribbean Sea, in the western portion of the Atlantic, will have an impact on what occurs in West Africa or even Florida later in the season. How we experience these very unpredictable kinds of phenomena can be problematic at times. We have to find the means of being able to observe, hypothesize, or explain, and ultimately predict these patterns of weather. One of the only ways we've been able to do this is to look at it through the lens of climate. So the work of a climatologist becomes extremely important for us. Climatology, in this case, is the study of climate. It is the analysis of long-term patterns of weather and the experiences that we have in relation to those patterns of weather. It includes extreme weather events over time and over space. Now, climatologists will attempt to organize, categorize, classify, and ultimately predict these long-term patterns of weather. They do this by organizing them into climatic regions. So, a climatic region becomes a physical space where similar weather patterns, in a very predictable way, are expressed in a cyclical fashion. By creating climatic regions, what we're able to do is we're able to manage some of the extreme anomalies that can be associated with patterns of weather. It allows us as physical geographers to be able to plot out all of the phenomenon within a map environment. And we're able to do that so that we can then scientifically understand where patterns of weather might be leading us, how we might experience a December snowfall in a decade or 2 decades. These concerns become the concerns of climate and climatologists. Now, there is one climatologist in particular who becomes very important in our understanding of long-term patterns of weather, or in this case, climate, Vladimir Köppen. We'll be looking very closely at Köppen's climatic maps of the planet. In fact, these have changed very little over time. Köppen plotted out patterns of climate over physical spaces. He created what are referred to as heat zones. This was a concept that he coined in the late 19th century. Basically, this system, and it's something that we still use today, looks at long-term patterns of temperature and precipitation. It is a mathematical model, in a sense, that attempts to record and organize climates and climate types. Now, the climatic system that Köppen developed in the late 19th century is not identical to what we use today. We have added in a variety of new technologies, and we have also come to include the total annual pattern of precipitation for specific regions as we plot these out on our global map. But no matter if we're looking at a historic map, let's say of Köppen's own design or one that is being used today, maybe something directly from your readings. The thing we have to keep in mind is it is a taxonomic system. It's a system of, in a sense, naming, classifying, and of course categorizing different long-term patterns of weather. And these long-term patterns of weather are rooted in terms of variables associated with temperature and precipitation, both within short-term and long-term units. And these units, and we'll look at one here in just a moment, are then organized through a coding system. In this case, a system that will assign two different letters to each climate region or climate type. So the first group of climates that we'll take a closer look at, both in terms of describing them, but also looking at them in terms of where they appear on the planet, is often referred to as a tropical humid group. This group will be generally classified with the letter A. It occupies almost all of the land area that we associate with the tropics. It is also a climate type that is associated with areas of the globe that really are winterless in terms of their seasonal weather patterns. However, what you will find as you continue to pair your readings with the content of this lecture series is that the terms winter and summer will be used in all climate environments. However, the term winter or summer as it applies to a tropical climate environment, such as the kind we're looking at right now, really relates more to the time of year than how we experience weather during that period of time. So what is a tropical climate? Well, generally, a tropical humid climate type is one that is constantly moist. Rainfall is the highest among all of our climate types. In terms of things like storm activities, the kinds of extreme weather that people living in a tropical climate experience, convection forms of storm bodies are typical. So convectional thunderstorms are common to these regions. Convection thunderstorms are generally triggered by local patterns of heat, and usually the heat patterns are extreme. And then they will also be connected to another phenomenon associated with kind of the equatorial and subequatorial regions of the planet, these trade wind patterns, and where they converge geographically. Temperatures in tropical climates are generally high for all the months of the year. So if we take a look rather at all 12 months of the year and we record the average temperature for each of those months and then we average them across the entire year, we find that generally the temperature pattern will be well above 63 or 64 degrees Fahrenheit. We will also recognize that rainfall patterns are of the highest when we look across or compare a tropical climate type to others, those associated with mid-latitude environments or polar environments. Here we see an average monthly total for rainfall at being approximately 2 to 3 inches on average for each of the months. Now, a tropical climate will have subtypes, or there will be subclimate regions that will be part of our classification of this climactic region. For our purposes, we recognize three subclimate types. We recognize a tropical rainforest climate, or subclimate. We recognize a tropical monsoon subclimate, and again that was something that we discussed in relation to patterns of rainfall in June to September in places like West Africa. And then we recognize a tropical savanna subclimate. These subclimates and how we classify them are in a sense attempts to take the variability that exists within a tropical climate region and break it down into more usable units of measurement. So how does this look on a map? Well, if we take one of these subtypes, in this case a tropical rainforest environment, it will be inclusive of a variety of national environments and regional environments. We will recognize places like inland Brazil or Honduras or Guatemala as being part of this phenomenon. We will include other regions of the planet, including locations such as Sri Lanka or coastal Burma or even Sumatra as part of this phenomenon. But what we will find is that generally these locations will be considered to be both tropical and wet climates, and they will be predominantly equatorial in nature. Climagraphs, looking at monthly temperature and precipitation patterns, will recognize them to be generally hot and wet. And the rainfall that is associated with these particular subregions will generally be associated with that convective or convectional thunderstorm activity. These storms will be extreme. They will yield heavy rainfall in very short bursts of time. In our next lecture, we'll begin to take a closer look at other climatic regions and the subclimates within them.